let's say you're trying to find the most optimal workout plan, and the different hyperparameters, these are the different kinds of settings you can use are your exercise selection, the rep ranges you use, the different weights you're going to use, the amount of sets, and any other sort of criteria that would be involved in setting up your workout plan. Let's say that this grid, and in this grid, every single square represents a different combination of settings. So this square right here would be 8 sets of bicep curls with 50 pounds with 50% intensity for 3 sets. This square right here would be 275 pounds of 3 sets of squats with 25% intensity, and so on. So each square would be something different. And let's say your optimal plan, the plan that's optimal for you to put on as much muscle as you can, is mapped with this line. So this means that everything that the line touches is an exercise that you would use for your plan. Now, if you want to find the most optimal plan to use, one method is through grid search. So you can run through every single square in the entire complex, and then over time, you'll get something. You'll be able to map out the best optimal route. However, this is very slow and wastes a lot of resources. Another thing you can do is the random search. So you can look at random points along here, and then when the entire grid is filled up, you'll get an idea of what is the best method. Now, again, this wastes a lot of time and is very arduous and uses a lot of compute power. So a solution researchers came up with at the University of Columbia was Bayesian optimization. So how this works is you start with a specific workout plan, and based on the specific area you want to target, it will dynamically adjust the points that I've selected. So this is our workout plan that we're starting out with. And let's say after this workout plan, we look at our results and say, okay, this point here, it performed very well. So based on probability distributions, it would be the points that are also going to perform very well are somewhere within these boundaries. And then we can only select points within these boundaries. And it's still more or less random, but it's backed by probability systems. And over time, you can develop outlines that align very closely with optimal path. And over 25 renditions of this training program, you'll be able to correctly map out the entire workout plan. Let's say you're over here on the bench press, bench pressing. But then you notice, oh man, my shoulder kind of hurts. Instead of continuing to bench press, because this is not going to be the most optimal for you to grow your chest because if you're injured, you can then switch to chest flies, something which still promotes growth and is now more optimal for you. Instead of sticking with the hard-coded instructions, you are varying them based on what is most optimal for your specific use case. Now let's examine embedding models, and more specifically, word-to-vec. So basically, embedding models work by taking each individual word in a sentence and assigning them with a vector value. When humans think of the word cat, we think of the nice, fuzzy little creatures. But, the computer doesn't have any idea of what a cat is. It has no recollection or no experience playing with cats or seeing them. So the only way it can understand them is representing them with the vectors. And the more related words are, the closer their vectors will be aligned. You'll see here, when comparing different words and their vectors, we'll see king, queen, prince, these words which are very similar, have vectors which are very closely related. And then electricity and toaster are closely related to each other, but they are very far apart from these words which have some consistency within their context. So using the same sentence for both, we can look at the different methods in which word-to-vec operates. The first being skipgram. So basically how it works is, the goal of word-to-vec is to try to guess the next word in the phrase and give it some sort of vector that's associated with it. So skipgram works by starting with some center word. In this case, it's on being the center, and then it expands outwards from there. Based on its training data, it's going to go look at the probabilities of all the different words that are available and go, okay, well, if the words next to this word are probably going to be sat on or sat and then the, and then beside those would probably be cat and mat. Assuming it was only trained on this phrase, or this phrase came up a lot in the training data that it was exposed to. Moving on, we have a continuous bag of words, or CBO, I'm not sure how to pronounce it, but this is the converse. So here we start with the full sentence, and by averaging these vectors, you'll end up with some average vector. You'll end up with some average vector, which represents a word, in this case being on. Skipgram tends to use a lot more compute power because instead of calculating, one word like we are here, it's calculating 1, 2, 3, 4 in this example sentence. However, it tends to be a lot faster and a lot more efficient because just by using one sentence, we were able to correctly get the vectors of 1, 2, 3, and 4 words, whereas here we started with 4 and only gained 1 more. But now a question is, how does it actually go about this process? How is it turning these words into these vectors? So let's say we start with a continuous bag of words model. So if we have, cat sat on the mat, and we start with just the middle word, then basically it'll turn this into hot encoding. So we can start with a hot encoding, which is just a binary representation of what numbers are available and which are not. So you see 0, 0, 1, where the on is, and then 0, 0. And then we can multiply that by a weight matrix, and then we'll get some vector in our semantic space. So this is, I'm just making it up on the fly here. We have negative 3.2, 1, 0, and 5.3 and 2.2. So this represents our sentence, in a semantic space. So when looking at training machine learning models with Bayesian optimization, more specifically, especially embedding models, we define an optimization target, which is usually an evaluation metric based on some downstream task. Let's say for now it's the performance of some test, which we'll say is Simlex 999. And these are the different hyperparameters we can use. So we have semantic density, local window size, sentence length, etc. Anything that can be varied to help the machine learning model. So if these are the optimal path for the settings in training our model, we dynamically adjust the settings based on the performance. Over time, we'll get something that closely resembles the actual optimal path. And over 20, 50, however many renditions, we'll get something that mimics the exact path. And so you know when to stop when the performance tends to plateau. Once this line becomes fully optimized like this, then reducing its thickness so much you can't even see that because I'm going over it in my highlight, but it doesn't actually improve the performance at all because performance has plateaued. We have found the optimal path. So when creating these sort of optimizations and defining our search space, another thing that we have to look into when running our Bayesian optimization model are our surrogate and acquisition models. So basically, the surrogate model, this will define the bounds that we're looking for. So if we look at our search space here, let's say this is the optimal, and let's say we have one point that's here. We have one point that's here, a couple more spread out. The surrogate model uses a Gaussian distribution system to create these sort of boundaries. These yellow highlights here that I'm creating, these are defined by the surrogate model. And it's mostly defined by using a Gaussian distribution such that the area between distributions is about 2 sigma. Right there. All right, so next, moving on to the acquisition model. This is the model that predicts where the red dots after it, after the surrogate model has defined the bounds, where the next red dots are going to go, where it's going to explore next. And here there's a lot of liberty you can take. So if we use an expected outcome system, this is a system that's better to outperform than the last dot placed. So let's say the last dot was placed here. It would want to choose something that is most likely to perform better than the last dot. So this is something that prioritizes performance rather than exploration. And now we have something called an upper confidence bound. Basically, the upper confidence bound will either tend to go for areas which are less explored. So right here there are no dots, we'll go around here. Or, depending on user specifications, it'll stick to areas which are more likely to perform. So you get a lot of flexibility whether you want to prioritize exploration or pure performance, depending on the limitations you're working under. All right, let's look at the steps for Bayesian optimization. So the first thing you want to do is define your hyperparameters. So these would be the settings that you'd want to tweak. So these would be things like local context, local window size, semantic density, length, etc. And then the next thing you want to do is define your objective function. So this would be the thing that you're actually trying to optimize. In the example of creating a workout plan, it was to maximize muscle growth. For actual machine learning models, it most likely takes the form of some evaluation metric, which is used as an indicator for how well it is going to perform in downstream tasks. So let's say you wanted to use an embedding model to train another model downstream, an NLP model, a natural language processing model, to analyze bias in news source claims. So something like a semantic similarity would be very important. So using a score like SIMLEX999 would be very important. The next thing you want to do is run your Bayesian optimization. Now, this is generally how the workflow looks. So basically, imagine you have some corpus. This is the text that you're going to be training your machine learning model on. Let's give it some general book corpus. So it's just some book transcript. Basically what's going to happen is the weight matrix that turns those hot encodings to actual vectors, that is going to be tweaked based on the training data every epoch. And an epoch is just defined as every time the full corpus is ran through the model and averages are tweaked. So every time this full text is ran through the model, it's going to be tweaked. The weight matrices are going to be tweaked according to every corpus. And then according to every epoch, and after the full epoch, what will happen, this defines a training cycle. So this will just continue repeating for however many training cycles. Let's say n is equal to 25. This is going to repeat 25 times, and each time we're going to tweak our hyperparameters, which were defined in our search space here, which would be these right here. So that's generally how the workflow looks. The next thing we can do is we can analyze the results. So after you found an optimized split, you create your graph. After you optimize your model, your graph of error over time, you start with pretty high error and then it'll sort of taper off as it plateaus. And right when it gets to about here, and this is delta t, and this is error. So right as we get to around this region here, notice that it's sort of tapering off, and this indicates optimization has occurred. So once you reach this region, you can actually analyze the hyperparameters, look at the search space directly and what parameters it actually ended up choosing. The next thing we want to do is visualize the scores, and that's just plotting our errors over time with a nice neat little graph right here. Alright, now let's look through the actual implementation code of our Bayesian optimization system. So here you'll see our import statements, and then the first thing that we're going to do is actually load our data. So currently right now we're just using text8 is some corpus from the Genism library, or GenSim library, as our example corpus, as corpus that the corpi that we use for the age of acquisition project will be defined later. And then we'll see the eval file paths. We're using two eval methods, one of them being the Google analogy test and the other being SimLexNine, SimLexNine being for pure semantic similarity. And then the next step we're going to do is define our hyperparameter search space. So this is what we're talking about when I talk about defining hyperparameters. Here we're telling our Bayesian optimization algorithm the exact different properties that we want to change and what we can change them by. So here it can change it between 50 and 300. It can change the vector size by 50 to 300. The window count between 2 and 10 words, and so on. If we want to choose between skipgram and cbow, here we have it so that the Bayesian optimization system will automatically choose the best one. That's part of the optimization process, but if we want to hard code it, then we can change this just by removing one of these numbers. The next step that we're going to do is actually create our objective function. And this is the thing that allows us to actually optimize the specific thing that we optimize. So here the code is written so that we have two optimization pathways, one of them being, these are our parameters, one of them being the Google analogy test. And so it's just a very simple if statement to see if the result is better than the last one. And the same thing goes for the SimLexNine. And because we want to minimize a negative correlation, we're going to be using the negative Spearman correlation here. We're going to be wanting to use the negative accuracy because we want to minimize the negative. This is just to conform which evaluation method we want to use when actually running the Bayesian optimization system. And here we can define our statements to run the function. So this is the number of training cycles that we're going to use. Here it's set to 25. It must be set over 5. So let's see if I set this to 3. So Python optimize word to back.py. We run that. You'll see that there's an error that calls cannot be under 5. So let's just keep that at 25 for now. And here we can analyze the results. And then we can visualize them by plotting our evaluation metric over time. So hopefully you have a better understanding of how Bayesian optimization works, and you can even use it in your own projects.